So we have lecture 67, ellipses. So this is just purely going to be mathematical, okay? Got plenty of pens. So let's start with something that we know, or we should know rather, really well, which is, of course, a circle. So I'll pick some radius. Let's make it 2. All right, so this point, 2 units away. This would be 2 units away, 2 units away, 2 units away, something like that. So, some semblance to a circle anyways, right? And so, who remembers the formula? Can anyone tell me the formula for this circle? If I call this my x-axis and this is my y-axis.
You mean the area of the circle?
No, not the area. I want the formula for the circle. Who remembers the formula for the circle?
I don't remember this. You mean the circumference?
No, I mean the formula for the circle. So, for example, the formula for a hyperbola, right, is y equals x squared, right?
Yeah.
And so we recognize hyperbolae, or hyperbolas, I'm not sure. Or excuse me, not hyperbola, parabolas. The formula for a parabola is y equals x squared. We recognize when we see y to the first power, x to the second power, we're like, oh, this must be a parabola that we're talking about, right?
Yes.
So
Y equals x.
that would be a line. When we see y and both y and x, both to the first power, we think line. Well, if we have x squared plus y squared, and that is equal to, I'll write it as 2 squared, right? 2 squared, the radius squared, right? This is the formula for a circle, right?
Yeah.
And it's basically just saying, pick a point, right? Let me use a different color here. Pick a point, and let's draw this little triangle here, right? So we can go over, so this will have the coordinates x comma y, this point, right?
Yeah.
It says that, well, x squared, which is this distance down here, right? There's x, plus y squared, which is this distance right here, right? Is equal to r squared. Well, I should have used something maybe the size of this pen. If this is r, right, what defines the circle is that every point on the circle is a distance r from the center. Okay?
Okay.
And so, from the Pythagorean theorem, we have the algebraic formula for a circle. Okay?
All right.
Now, of course, I can rewrite this. Instead of saying 2 squared, I can just say, well, that's just 4, right? Yes?
Yes.
And then I could say, well, maybe I'll divide everything by 4. So I'll have x squared over 4 and y squared over 4. And this, of course, becomes 1. Yes?
Yeah.
Right? So that's the formula for a circle also, right, in another form.
Yeah.
So what is the formula for an ellipse? What do we do to make an ellipse? Well, to make an ellipse, let me get rid of my label here. To make an ellipse, what we need to do, let me get rid of these notes here as well. If I take this circle and I stretch it out a little bit, right,
Yeah.
such that we can imagine it might look something like this. I think that's okay, right? So what I've done here is I've stretched this guy out. Now, in this direction, everything seems to be the same, right? But in this direction, right, we can modify this by saying maybe this becomes, oh, I don't know, what did I use in my notes? 25, let's say. Right?
Yeah.
So what is that, 25? Well, it's 5 squared. So let me write this as 2 squared over 5 squared, just to be extra clear. 2 squared, 5 squared, right?
Yeah.
So now I have what we call an ellipse, right? It's basically a circle that's kind of stretched. We can generalize this and write the general formula for an ellipse as follows. It would be x squared over a squared plus y squared over b squared equals 1. That's the general formula for an ellipse, okay?
Okay.
Now we're going to stick to a convention that anytime we have an ellipse, maybe we get an ellipse that looks like this, right?
Yes.
We're going to take our coordinate system and rotate it, or we're going to take the ellipse and rotate it so that it's flat like this. So the long side
Yeah.
is always in the x direction, okay? If that's the case, then what we're going to say is that A is always greater than B. If it's equal to B, it would be a circle, but, right?
Yeah.
You can see that. The ellipse, I'm going to get rid of the circle if you don't mind.
Don't.
The ellipse is going to have some special points, and I want to point these out to you. I guess I should have probably motivated why are we talking about ellipses, because we're going to use them to some degree when we talk about Kepler's laws in more detail, and also when Newton's approach to working with Kepler's laws. Okay?
Okay.
So ellipses will be important. So I just want to get the terminology down so that we know what we're talking about when we hear it.
All right.
Okay? All right. So there are some important points to label on this ellipse. One point we'll call the focus of the ellipse. And you can think of this as what used to be the center of the circle, and as you stretched it, right, that center point separated into two center points and went out like this. Okay?
All right.
That's the way to think of it. Okay? But so every ellipse has two foci. And I'm actually going to call this focus F prime, just to distinguish it from this one. But the distance from here, this distance here, we're going to call this distance C. Okay? Actually, I want to write it in a slightly different location. I'm going to write it down here. So the distance from between the origin and either foci, either focus, is C. Okay? Another important points are the vertices and covertices. These we call the covertices. I'll call it, I guess one is a covertex, I guess. Covertex. And these we call vertex and vertex. And this, of course, is again a covertex. So the vertices and the covertices. So the vertices, as you can see, lie at y equals 0, right, as we've drawn here. So if y is 0, right, what is this? Let me just change this to a squared and b squared. A squared and b squared. So if y is 0, this gives me that x squared over a squared equals 0, plus 0 equals 1, or x equals a. Okay, really plus or minus a, because we took the square root of a squared, right? So plus or minus a. So we can be here or here. So these points, the vertices would be at x equals a, y equals 0, and x equals minus a, y equals 0. Okay?
All right.
Similarly, the covertices we can find because they lie where x equals 0, right? X is 0 here, x is 0 here. So we get that y is equal to plus or minus b. So here, this point would be x equals 0, y equals b. And this point down here would be x equals 0, y equals minus b. Okay?
Okay.
So those are the vertices and the covertices. Now, of course, the defining property of an ellipse, just draw these lines in here. Do I label these points? I guess we could call this the point P. Okay, so this point is the point P on the ellipse. Okay?
All right.
And so the defining property of an ellipse is that F prime P, the line segment F prime P, plus P of F P is equal to a constant.
All right.
So F prime P, that's this line here, plus this line here is equal to a constant. So wherever I move the point P, it's going to be equal to the same value. So I want to find what are the coordinates for the focus. What is C equal to, right? This distance C. How do I find that? Well, if we look at this, we see we have a right triangle, two right triangles, right?
Yeah.
And let me just zoom in on these right triangles, one of them anyways. Here's our point P. Let's write that as point P. Here's our point F prime, right? Here's the distance C, right? This is where our origin was, right? O. The height of this is the distance B, right? Because this is x equals 0, or excuse me, y equals 0. This is y equals b. So this side length here is b. What is this side length here? Who can tell me that?
C
This is, go ahead.
the square root of c squared plus b squared.
Yeah, that's right. So this side over here is the square root of c squared plus b squared. And so what is this constant in this case, right? So in our case, as we've drawn it, the constant will be equal to, you see this will also be the square root of c squared plus b squared.
Yeah.
So it's 2 square root of b squared plus c squared. Doesn't matter which one is first, b or c. Now I want to consider moving the point, right? So this is if we let p be equal to, so this is what we get when p is equal to the point 0 comma b, all right?
All right.
What if I move the point over here, right? I'm just going to draw a separate picture. So that'll be the point. What if p is equal to, that will be at minus a comma 0, right?
Yes.
And so let me just draw. Here's my ellipse. Here's this point F prime, and this is the point F. This distance is C, this distance is C. This point where P is now is at minus A. So this is a distance of A, right?
Wow.
So this from here to here, right? This is the distance A. Yes?
Yes.
So to go from F prime, right, to P, here we went from F prime to P here. Now we're going to go from F prime to P over here. So what is that distance? How long is that? Well, that
That's A
is
minus
A
C.
minus C. But we also have to go from point F, right, from the focus F, all the way to here, right? So we'll cover that distance again, right? So we'll have 2 times A minus C, plus we'll have this distance and this distance, right? 2C. So plus 2C. Yes?
Yeah.
So if I add these up, right, I have 2A minus 2C plus 2C. The plus 2C minus 2C cancel, right? And so I'm just left with 2A. Okay?
All right.
So I can now determine what C is in terms of A and B, these constants of the parabola. Okay?
All right.
I know that this distance is equal to 2 times the square root of B squared plus C squared.
Yeah.
That's when P is at 0B. And it's equal to 2 times A when it's at the point, when P is at the point minus A0. Okay?
Okay.
These two distances have to be the same. Right?
Yeah.
So that means what? Means that 2A is equal to 2 square root of B squared plus C squared. Yes?
Yes.
The 2's will cancel, right? So you get rid of the 2's. And what I want to do is I want to solve for C. Okay?
All right.
So how can I do that? Well, I can square everything, right? That gets, turns that into A squared. It gets rid of the square root, right?
Yeah.
So that says that A squared equals B squared plus C squared,
Yes.
which means that C squared is equal to B squared minus A squared, right?
Yeah.
Wait, hang on a second. I got that wrong.
Well,
I double moved it in my head. A squared minus B squared. There we go. Right?
yes.
Now I can take the square root. So this says that C is equal to the square root of A squared minus B squared. Yes? Just some algebra, right?
Uh,
So I've solved for C. I now know what C is. So that's a good thing. But what I want to do now is I want to play with this a little bit, and I want to introduce a new factor, okay, which we're going to call the eccentricity. Okay, apparently there's more than one way. There's more than one definition for the eccentricity. There's like an angular eccentricity, a linear eccentricity. There's a variety of different ways to quantify how eccentric this triangle, how eccentric this ellipse is. Okay,
okay.
so by eccentric I mean not circle-like,
Yeah.
right?
Yes.
And so like one way, a simple way would be to say, well, it's just the ratio of, A over B, right? They usually call A the semi-major axis. Well, yeah, the distance A they call the semi-major axis, I guess. It's from here to here, semi meaning half, right?
Yes.
So from here to here, that'd be 2A in distance, right? So A is a distance, it's the semi-major axis distance. And the semi-minor axis, I think that's what they call it, is 0 to B, right? That's the semi-minor axis, okay?
Okay.
So you could take the ratio of B over A, or A over B. Either one would work. If it's not one, it gives some measure of eccentricity. But we're going to define it like this. I'm going to take this expression here, right? I'm going to factor out an A. So we'll get C equals, I'll just do it, we'll have I'll have A squared times 1 minus B squared over A squared. Right? So if I multiply this through using the distributive property, A squared times 1 is A squared. A squared times minus B squared over A squared is just minus B squared, right?
Yeah.
Nothing tricky here. Then I can pull out this A squared, right? Because what is the square root of A squared? Well, it's A. So this says that C equals A times the square root of 1 minus B squared over A squared. I guess this is that other eccentricity factor that I was talking about before. And now what I want to do is I want to divide out A on both sides. And I'm going to put this over here. And we define this as the eccentricity, E, is equal to C over A, which is equal to 1 minus B squared over A squared. Okay?
Yeah.
That is called the eccentricity. So if you're looking at someone cites the eccentricity of, say, some orbit, like maybe Mercury's orbit or Pluto's orbit or something like that,
Yeah.
and you want to like draw it, this is the eccentricity they're talking about, I think. Whoops, sorry, right here. Okay,
All right.
so this is what you would give. You say, well, E is equal to whatever value they give you. You can then figure out what A and B need to be and where your foci are going to be on your ellipse. Okay?
Okay.
Yeah, so if we look at this for a minute, think about it. Well, if it was a circle, that means that A and B would be the same, right?
Yeah.
And so 1 minus, well, B squared over B squared is 1, right? So 1 minus 1 is 0, which means the eccentricity is, if B is equal to A, what's the eccentricity?
0.
0, right? So circles would have an eccentricity of 0, okay?
Okay.
If it's greater than 0, remember I said that A is always greater than B, right?
Yeah.
So what does that mean? This means this is always less than 1, right?
Yes.
Because A is less than, A is bigger than B. Did I say less than B? I probably said A is less than B. A is by definition for us always greater than B.
All right.
Right? We always want to orient the ellipse so it's long ways like this and not like this, right?
Yeah.
So given that, our eccentricity is reserved to be between 0, if that's if A is equal to B, which I guess technically isn't allowed with the A greater than B rule, and going up to not quite getting to the eccentricity can get close to 1, okay, but not get to it.
All right.
Right? Because we have 1 minus, and we can make this as small a thing to subtract from 1 as we want. Okay, so it could be 0.9999999, you know, forever. Yes? Okay, so the last issue we're going to talk about is called the latus rectum. Latus means straight, rectum means right. I'll show you what it is, though. Newton references it, and so this is the reason why I'm mentioning it. But we need to declutter a little bit. So let's make a note that the eccentricity E is equal to C over A, but it's also equal to the square root of 1 minus B squared over A squared. So what is this latus rectum? Now, this is in reference, this is terminology I think that comes from Apollonius, who was, I think, a contemporary of Pythagoras. Maybe it was later. Probably it was later. It must have been later. I'm not sure. And so he would define the conic sections in terms of directrix. You've probably seen this before with reference to a parabola or hyperbola,
Yeah.
right? And for a parabola, for example, we have a focus for the parabola. We'll have a directrix, which is a line. It's a terrible, terrible line. And the distance from the focus of the parabola to any point on the curve itself plus the distance from that point to a straight line to the directrix, right, is a constant of the parabola. Okay, that's a defining quality of the parabola. The ellipse can be defined in a similar way using a directrix, which would appear on this side like this, as a vertical line over here, and another one on this side, a vertical line over here, one for each of the foci. Whoa, one for each of the focus. No, one for each of the foci. It's plural. And so the latus rectum is parallel to the directrix. Okay.
All right.
We're not going to use the directrix, so I'm not going to bother deriving how far away it is from the center of the ellipse. Okay, so how do we find this point? Well, look at the point, right? We know that the x value of this point right here, right, is c, and y value is 0. So this point is c0. How high up does it go here? What is the y value here? Well, it's just some value L, and we'll call that value L the lattice rectum. I think they call it the semi-lattice rectum, because the full lattice rectum is from here to here. It's like a line that is parallel to the directrix that passes through the focus. That's probably how it's defined. Okay?
All right.
So we'll concern ourselves, though, with the semi-lattice rectum. So we want to take our standard equation for the ellipse, and we want to let x equal c, and we'll let y equal L. Okay? So what does that give us? That gives us c squared over a squared plus L squared over B squared equals 1. Right?
Yeah.
So what I'm going to try to do is derive a formula for the lattice rectum, okay, which Newton references. Let's multiply everything by B squared. I'm going to multiply everything by B squared. That will give me c squared b squared over a squared plus l squared equals b squared. Now I'm going to solve for L squared. That'll give me L squared equals B squared minus C squared B squared over A squared. We're probably okay. I'm going to factor out a B squared over A squared. So I'll get L squared equals B squared over A squared times, that'll be, well, for this quantity, right, we already have the B squared, so I have a 1 up here. But we're going to have an A squared in the denominator, so this really needs to become A squared, right?
Yeah.
So B squared over A squared times A squared is going to be B squared, right? Minus, here, I need a B squared and an A squared in the denominator, and it just leaves the C squared behind. You know what I think I want to do? I want to leave the A squared in there. Okay, so this just becomes 1. There we go. That's what I want. Because I'm looking for a C over A, right? I want to get a C over A in here because now I can write this as L squared equals B squared times 1 minus E squared, the eccentricity. You see that?
Yeah.
Which means that L is equal to B times the square root of 1 minus E squared. That's a terrible E. Let me fix that. There. Okay?
All right.
So we see that the lattice rectum is related to the eccentricity, right? So I'll write L equals B times the square root of 1 minus E squared. Now, if I want to, I can derive another expression for this, a more common expression for this, I guess you'd say. Instead of putting E in there as I did, you might recall from before that here we had, yes, when we defined the focus from this point here, we had the result that C squared plus B squared equals A squared, right?
Yeah.
Remember that?
Yeah.
Which means that A squared minus C squared is equal to B squared, right?
Yeah.
So if I look back to this point here, where do I have an A squared minus C squared though? Oh goodness, I know it's here somewhere. All right, let's see. Now I know how we can get that. Yeah, so if I write L squared equals B squared over A squared, then I get A squared minus C squared. There it is, right? And A squared minus C squared is just B squared, right? Do you remember how we got this? We considered a point P right here, and we defined the distance, right? Where this would be the distance C. This is the distance B. And this side length, right, is the square root of B squared plus C squared, right?
Yeah.
And then we related it to the same thing when the point P was over here. Do you remember that? I should have left it on the board, but I took it off. But this was the result that we got, right? Was that A squared minus C squared is equal to B squared.
Yeah.
Okay?
Okay.
And so I'm using that here now. So I'm going to replace A squared minus C squared with B squared, and so I get that L squared equals B squared times B squared, which is B to the fourth, right?
Yeah.
So B to the fourth over A squared. I can take the square root of that, that's B squared over A squared, or it's B squared over A rather, okay? So the two kind of standard ways to define what the lattice rectum is, right? Lattice rectum. And, but it has to do with it's a constant of the ellipse
All right.
and related to the eccentricity. Okay?
Okay.
And so that's all the information we need going forward with ellipses when we talk about Kepler's laws. So I'm going to stop it right there. Okay?
All right.